Welcome to Unit 4 of Analytical Chemistry 2 paper in the 4th semester of a second year B.Sc Chemistry course at Dr. MGR Educational and Research Institute. In this unit, we are going to see ESR spectroscopy. In other words, it is also called as EPR spectroscopy. Now, what does ESR or EPR means? ESR stands for electron spin resonance and EPR stands for electron paramagnetic resonance. So this ESR or EPR spectroscopy is also called as electron magnetic resonance spectroscopy, abbreviated as EMR spectroscopy. So in general, we can say that it is a branch of absorption spectroscopy in which radiation having frequency in the microwave region is absorbed by paramagnetic substances to induce a transition between energy levels of electrons with unpaired spin. So the principle is same like that of the NMR spectroscopy, where in NMR we use radio frequency electromagnetic radiations, and here we use microwave frequencies. So that is the difference between NMR and ESR spectroscopy. So when we talk about the spins and the magnetic field, we know that the spinning objects will have a magnetic field also. So we can very well see in the picture that when an object is spinning, it has a magnetic field also. As the earth rotates on its own axis, it has got a magnetic field strength. So such like that, all objects which were rotating on its own will have a magnetic field around it, and the Hand's rule, like Fleming's rules, will demonstrate the direction of the magnetic field of the motion with respect to the motion of the objects. Let us consider the spin of electrons. If we consider an electron is spinning in a clockwise direction and a magnetic field is perpendicular to it, represented in an upward direction by the arrow mark, the magnetic field will be in the reverse direction to it, exactly opposite to that if the spin of electrons is in anti-clockwise direction. So that we represent here that if ms is equal to plus half, the magnetic quantum number is plus half if it is in the clockwise direction. It will be minus half if the spin is in the anti-clockwise direction. So if the magnetic field is in the upward direction for plus half spin quantum number, the magnetic field will be in the downward direction, exactly the reverse of it, if the magnetic quantum number is minus half. So we represent the spin of electrons, magnetic field and magnetic quantum number in this way. Let us talk about the magnetic property of elements. If an element has electrons paired up and the spinning is in opposite direction to each other, that is, if one is in plus half, the other is in minus half magnetic quantum number, then the total magnetic quantum number will be 0, and that will contribute to a diamagnetic character. So such elements cannot be studied with ESR and EPR spectroscopy. The reason we will find it out shortly. The other part of a magnetic character is paramagnetic one, where if elements or a compound has electrons unpaired and the spinning is in the same direction, or if it has odd number of electrons, like only one electron or 3 or 5 electrons, something like that, like in free radicals or transition metal compounds, which have G electrons unpaired and the spinning is in the same direction, then the total magnetic quantum number will not be zero, and that will contribute to paramagnetic property. So such compounds or elements, when subjected to external magnetic field, the spinning direction of the electrons will align itself to that of the external magnetic field direction, which means it will be in a parallel mode, and the spinning can be represented as minus half when it aligns to the external magnetic field direction. The same when we are subject to microwave radiations. When after passing external magnetic field, when we pass microwave radiations, the spin of it will get reversed. That is, if when first the spin is minus half, after passing microwave radiation, the spin will change to plus half, exactly the opposite to the one. So what happens here is, because the spinning changes after passing microwave radiations, a resonance occurs. The resonance of spin occurs with that of radio waves and paramagnetic behavior. So that is what we call it as ESR or EPR, and the study is ESR spectroscopy or EPR spectroscopy or EMR spectroscopy. So we are dealing with the spin of the electrons, the paramagnetic property, and the resonance of it with respect to microwave radiations. In this slide, we are going to see the splitting of electrons in two different energy levels when subjected to an external magnetic field. Before application of the magnetic field, the spin of the electrons can be plus half or minus half. That is, the spin can be in either of the directions. When it is subjected to an external magnetic field, it aligns to the magnetic field direction and the energy will be lowered, and if we say ms is equal to minus half, the energy is lowered here. But what happens is, after passing the external magnetic field, the ms is equal to minus half is changed to ms is equal to plus half, which means the electrons go to the higher state, higher energy state, and the spinning is also being opposed to that of the previous one. So degeneracy of the states happens here, and the energy difference between them is given as a delta E, which is equal to G mu B, where G is the Landis splitting factor, or called as the proportionality factor, and mu is the Bohr magneton. Capital B naught is the strength of the external magnetic field we apply here. Having seen what is ESR, now we'll talk about the principle of ESR, or the EPR spectroscopy. So when an electron is placed within an applied magnetic field B naught, the two possible spin states of the electron have different energies. The lower energy state occurs when the magnetic moment of the electron is aligned with the magnetic field. The absorption of energy causes the transition of electron from lower energy state to higher energy state. The energy of the state is given by E is equal to Gms mu B naught, where G is the proportionality factor called Landis splitting factor, Ms is the spin quantum number, which can be plus half or minus half, mu is the Bohr magneton, and B naught is the magnetic field, which we have seen in the earlier slide. So we can see that before application of the external magnetic field, the spin quantum number can be Ms is equal to plus half or minus half, which means the energies are not degenerated. And only after applying the external magnetic field, the two states appear here, two energy states appear, where one is the lowest state, which have the magnetic quantum number of minus half, and the highest state has magnetic quantum number of plus half. So the splitting of the degeneracy of the states also can be seen in the below figure. This is the instrumentation of Vss spectroscopy. We start with the source of microwaves produced by a klystron tube, and this pass on to the attenuator and waveguide such that the microwaves pass on to the sample holded by the sample cavity or the sample tube. And this is surrounded by electromagnets that produces the magnetic field. In this instrument, radio waves of a certain frequency is passed on, and only the strength of the magnetic field is varied. The modulation coils helps to vary these things, and finally a detector is used to find out the resonance of the spins and the magnetic behavior. Let us see the components of instrument of the ESR spectroscopy one by one, starting from the source. It's a klystron tube that acts as the source of radiation. Microwave radiation is typically produced and amplified by klystron tubule, which is capable of tuning waves to precise frequency, amplitude, and phase. These microwaves are then channeled into resonance cavity, which holds the sample by using either waveguide or coaxial cable. So the motion of charged electrons from hole in anode to reflector and back to anode generates an oscillating electric field, and thus electromagnetic radiations are generated. So we can see the picture or the schematic picture of the klystron tube here. Listed here are a few more components. Attenuator is the one used to adjust the level of microwave power. A waveguide is used to convey the microwave power to the sample cavity that holds the sample. So sample cavity is used such a way to maximize the applied magnetic field along the sample direction. And most ESR spectrometer have a dual sample cavity, one for the sample that holds the sample to be analyzed, and the other is for standard material. The standard material here is DPPH. Electromagnets of varying magnetic field is used here, and the magnetic field is varied through resonance condition by sweeping the current supplied to magnet by power supply. So modulation coils are used. The variation of magnetic field is produced by supplying an AC signal to modulation coils oriented with respect to samples. The detector used here is a commonly crystal detector of silicon, which acts as a microwave rectifier. So these are the components of ESR spectrometer. Let us see few applications of ESR. In the beginning, we saw that paramagnetic substances are subjected to the ESR spectroscopy. So compounds having free radicals or transition metal complexes where d electrons are not paired up can be studied very well with the ESR spectroscopy. So ESR is helpful in transition metal complexes to find out the nature of the metal, and the number of ligands in the complex. The geometry of the compounds can be found out. The number of d electrons present in the complex also or can be found out by this. So few examples we can see now. The first example is the chromium 3 plus metal complex. In case of chromium 3 plus, the spin degeneracy is removed by crystal field and the sublevels are not equally placed. So the resonance occurs at different frequencies. Further, if the paramagnetic ion has a nuclear spin, each sublevel will further split into the separation between splitted sublevels provides information of the hyperfine constant. So we do not consider only the electron spin, but also the nuclear spin is also considered here. So the nuclear spin will attribute to hyperfine splitting. So that's what we see in the figure, that the sublevels of minus half is being further splitted into minus 3 by 2 and plus half is further splitted into plus 3 by 2. So this study provides information about the type of the ion and the symmetry of this chromium 3 plus crystals. The second example is manganese 2 plus ions. If manganese 2 plus ions is subjected to the ESR spectroscopy, the spin orbit coupling will be 0, and on applying magnetic field, the ground state will further split into sublevels, so 6 sublevels. So since the separation between the sublevels is the same, all the resonance occurs at the same frequency. Let us see the key points of this ESR spectroscopy. The spin of the electrons and the paramagnetic behavior of the elements or compounds are considered here. The degenerated energy states after applying the magnetic field and the resonance of the spinning of the electrons with respect to these two energy states after passing the microwave radiations are considered as the principle here. The instrumentation of the spectrometer is also seen elaborately. Application to transition metal complexes like chromium and manganese are also seen. Cluster-like compounds can be subjected to the ESR spectroscopy to find out the number of electrons, the geometry of it. So this is not limited to ESR spectroscopy. It is just an introduction of the ESR spectroscopy to the UG program. So don't think this is just the end of that. We have just started to know about the ESR spectroscopy. So further reading, refer to many more textbooks of ESR or EPR spectroscopy. Thank you.